Assalamualaikum and hi, my name is Mohamad Haziq bin Kamarudin. So in this video, we will be presenting for our group project for energy planning for sustainable development costs. Our group member consists of three members, including me, then Mohamad Iman Danial bin Mohamad Firdaus, and Mohamad Jauhar Shaqili bin Johari. Our title of the project is Optimal Utility Planning for a Chemical Plant, Electricity, Steam and Renewable Energy Solar Integration using Multi-Period MILP. So without further ado, let's proceed with the content. To begin with, chemical plants require reliable electricity and steam throughout the year. Electricity is used for equipment such as motors, pump, compressor, and control system, while steam is required for heating and separation process. Traditionally, these utilities are supplied by grid electricity and natural gas boiler, which expose the plant for energy price fluctuations and carbon emissions. So therefore, this project evaluates a hybrid system involving the grid electricity, solar PV, natural gas, and biomass. Moving on to the program statement of the project. So currently, the current plant mainly depends on grid electricity and an existing natural gas boiler, which resulting in high operating costs and carbon emissions. So in addition, electricity demand, steam demand, and solar generation vary every month. So therefore, a fixed planning decision is not suitable when the main problem is to determine the best utility combination and monthly operation while meeting demand, investment limits, cost saving targets, and emission reduction targets. So the study covers a 12-month planning period and focus on electricity and steam supply, where the energy sources considered are grid electricity, solar PV, a natural gas boiler, and biomass boiler. The model is developed using mixed integer linear programming in software games. And then the main objectives are to minimize the total annualized cost, determine the optimal equipment investment and monthly dispatch, and achieve at least 10% cost saving and 30% emission reduction. Moving on to the project parameter. So the model uses demand, economic, technical, and environmental parameters, where the annual electricity demand is 10,320 megawatt hours, while the annual steam demand is 50,800 tons. Important economic inputs include the grid tariff, fuel prices, operating costs, and equipment capital costs, while the technical parameters include boiler capacity, efficiency, and equipment lifetime. So the model also uses grid and solar emission factors and 50 million budget and an 8% discount rate. The objective function is to minimize the total annualized utility cost. This consists of the monthly operating cost for grid electricity, solar operation, natural gas, biomass, and boiler operation, together with the annualized equipment investment cost. Then the continuous decision variables represent monthly grid electricity, solar electricity, steam generation, and fuel consumption, while the integer variables determine how many new solar, natural gas boiler, and biomass boiler units should be installed. Next, we move to for the our constraint. So several constraints are applied to ensure that the solution is realistic. Where firstly, grid and solar electricity must satisfy the electricity demand every month. And then natural gas and biomass steam must also satisfy the monthly steam demand. Then fuel consumption is calculated based on steam production and boiler efficiency. And then the additional constraint limit generation according to installed capacity and equipment bounds. And finally, the model must remain within the investment budget and achieve the required cost saving and emission reduction.
For the solution methodology, this project used a multi-period mixed integer linear programming or MILP model. Since all equations are linear, the optimization can be solved efficiently using GAMS mixed integer programming solver. The optimization model was implemented using GAMS. First, all monthly electricity demand, steam demand, equipment and specification, cost and emission factor were entered into the model. Next, the objective function and all engineering constraints were formulated, including energy balance, equipment capacities, investment budget and sustainability targets. Finally, the model was solved using the command solve utility planning using MILP minimizing Z, after which GAMS automatically calculated the annual cost, greenhouse gas emission, renewable energy contribution, and optimal equipment selection. This slide will summarize the computational workflow. The process starts with the collection of monthly demand data and all technical, economic, and environmental parameters. These inputs are formulated into MILP mathematical model before being solved in GAMS. The optimization then determines the optimal equipment configuration and monthly utility dispatch. Finally, the results are analyzed in terms of cost saving, emission reduction, and renewable energy utilization.
Moving on to the results of our optimization problem, through the GAMS coding, first we evaluate economic performance. We obtain an 11.75% of a cost saving from the initial of 8.5 million all the way down to 7.5 million. Other than that, we also did an environmental performance where we cut down 73.5% of the emissions from the initial of 17,000 tons of CO2 all the way down to 4,500 tons of CO2, thus making our plant future-proof and emissions friendly. So this is the newly optimized variables for our new plan. So from a pure reliant to on the non-renewable energy, the optimized version now is more focused on the renewable energy sources where the grid only covers 53.71% and the steam is fully generated by our biomass and the natural gas is a backup. Through our optimization problem, we found that the solar energy is actually cheaper compared to the grid electricity when we factor in its 25 years of lifespan. As a result, the solar actually provided a cheaper alternative at 150 ringgit per megawatt hours, which is around 45% cheaper compared to grid electricity and when you factor in all those tariffs. Moving on to our steam boiler, we found that biomass steam boiler is around 5 ringgit per ton cheaper compared to the natural gas steam boiler. And as in our assumption, alongside the one pre-existing natural gas boiler, there's only one more biomass boiler needed to be added in order to achieve this optimal solution. And so this is our sensitivity analysis for the optimized solution. So under our given budget of around the 8.5 million, we achieved this cost saving at 11.75% while achieving the 73 emissions reductions by installing 35 units. If given a bigger budget, we could install more solar units to achieve further emissions reduction and more cost savings. Furthermore, the boilers also have provided the 100% of the plant's steam requirements, thus they reach their blinding limit earlier. So in order to see more of the sensitivity, it is focused on the solar units.
This slide explains why the optimization selected the final utility configuration. The model installed 35 solar units because solar electricity has lower annual cost than grid electricity, making it most economical option for supplying electricity. It also selects two biomass boilers since biomass steam is slightly cheaper than natural gas steam and is sufficient to meet the entire steam demand. Therefore, no additional natural gas boiler is required. As a result, the optimized system achieved around 20% reduction in annual utility costs and a 70% reduction in greenhouse gas emission, while satisfying all technical, economic, and environmental constraints. Overall, the optimizer chose the least cost and most sustainable utility configuration for the chemical plant. Although the optimization model produced an excellent solution, it still has its limitation and also need a future improvement. First, the model used a monthly average demand data, which cannot capture hourly fluctuation in electricity consumption or solar power generation. Second, the model assumed a constant electricity tariff throughout the year. Then, the biomass fuel is always available at a constant price, and this model also does not include battery energy storage system or BESS. Therefore, a future work should focus on improving the model by incorporating hourly demand profile, realistic electricity tariff structure, battery energy storage system, and detailed biomass supply analysis. Overall, while the proposed model serves as reliable decision support tool for utility planning, this improvement will make it even more accurate and practical for real industrial application. In a conclusion, this project successfully developed a 12-month MILP optimization model for integrated electricity and steam planning. The model demonstrates that renewable energy technology can simultaneously reduce operating costs and greenhouse gas emission while satisfy all plant utility demands. Overall, the optimization model provides a practical decision support tool for future industrial energy planning. Future improvement may include hourly demand profile, real industrial tariff structure, battery storage system, and uncertainty analysis to further improve the accuracy and applicability of the model. I think that's all from our group for this presentation. Thank you.